What's up, everybody? Welcome back. In today's video, I'm going to be going over how to unify a query interface or have a unified query interface for your indices with Llama Index. So why would we want to have a unified query interface? At a high level, you can think of it as you need to query your indices, but you have different use cases. So you might have semantic search, just like you're asking a question about like a specific thing and it can pick up based off of the keywords in your query, versus like what I'm going to show you is and what we use in the example is a compare contrast composable graph. And with that, it's more like you're asking, when you ask a compare and contrast question, like what's the difference between A and B? What we'll do is we will decompose that query into simpler queries. So like, what is A about? What is B about? Okay, let's synthesize a new question like, all right, here's what we have that is A and B, and now let's find the differences between those. So that would be a different use case for querying your indices. It's not just a simple lookup question. It's more of like synthesizing an answer based on disparate data sets or disparate parts of data. So that's why we do it. And now I'm going to get into how we do it. And what we're going to be doing is going through a set of Wikipedia articles that we're just going to pull from the web. But just to get started, we are going to be using these 5 cities, and we're going to pull in all the text from each one, and write it to like a local folder that we have over here as the data. So Chicago's got TXT about Chicago stuff, and that is all cool. And now the next thing we're going to do is we need to keep track of each of the indices we're about to build. So how are we going to do this? We're going to make a dictionary or a mapping of the city docs, and each key will have a value of the list of documents about that specific city. So we're just iterating through and we're reading the text from each of these files here. Next thing we're gonna do is just build the service context. Not too much going on here. This is pretty straightforward. I'm just breaking out the functions just to make it more readable in the main function that we're working with, because it's a lot. So yeah, just define your LLM predictor. This is like the equivalent of the LLM chain or whatever, the wrapper for LangChain, just their generic thing. And we're going to be using OpenAI chat with the 3.5 turbo model because we're not trying to break the bank over here. And then we're going to get our service context just from defaults with a chunk size of 1024 and return it. So once we've done that, we're then going to get our vector indices from the city documents mapping we have. So passing in the titles of each Wikipedia article, the service context, and the city documents, because we're going to need those 3 to do this. So going into this function, the first thing we're going to do is we're going to build a vector store index for each list of documents we have for each city. So iterating through each title, we're creating a storage context for each vector store index we're going to create. And then we are going to be creating a vector store index for each city from the list of documents that we have for each city. So we're passing in the city docs, so the list of documents for whether it's Boston, Houston, Chicago, and we're going to be passing in the service context and the storage context. So we have the same service context, but each vector store index gets its own storage context. The next thing we're going to do is we're going to set the index struct index ID to the title of the article. And this is some good like prep for data before you load everything into the graph. But this is just for the for simplicity and for you to be able to see which index does what, and for the LLMs to know that as well. And then we're going to have persistent storage for each index. And return the vector store indexes. So there's going to be a mapping of vector indexes or indices now. And now we're going to define a graph So this is going back to the beginning of the video when I talked about the two different use cases. If you wanted to query just like a simple, like you had a question about Boston, we wouldn't need to decompose the query because it's pretty self-explanatory. Like, let's go find the information in Boston. If it's not there, then whatever. But if I'm saying what's the difference between the sports scene in Houston versus the sports scene in Toronto, then what you'll see in a second is the decomposed query transform under the hood is going to break that initial query into subqueries and then route those queries to the subindices, bring back an answer, synthesize an answer, and then continue on. So that'd be like, okay, well, first let's break that up. I need to know what sports in Toronto are like, and I need to know what sports in Houston are like. Go find that information, bring it back. All right, sports in Houston are mainly about football and, being around family. I don't know, I'm just making something up. And on the other side, Toronto's like, oh, sports are mainly about hockey, drinking beer, just hanging out with the boys. It's like, all right, what's different about this? Okay, that's the answer. And that's kind of how it works with a graph. But getting into the function, we're going to be passing in the titles again because that's how we're keeping track of all of this. Each of the mappings that we're creating have a key of the city's name. And we're passing in the vector indices mapping, and we're passing in the service context as well. Let's go build this graph. So for each graph, for the graph, each index is going to have a summary. And this is also for the query router in the query engine to know what each subindex is about. So for each title, we're going to add a summary to the index summaries dictionary or mapping. And we're going to say, this content's about whatever the title of the Wikipedia article is, et cetera, et cetera. And now we are going to build the graph, composable graph. From the indices, we have the root index class is going to be a simple keyword table index. And the children indices, we're doing list comprehension of each index within the vector indices and a list comprehension of the index summaries and max keywords per chunk. This is just set to 50. It's pretty arbitrary. I don't know what happens if you go too high, but I'm not trying to find out today. The next thing we're going to do is we're going to get the root index of the graph by calling graph get index graph.rootid. Sometimes when you follow along in the docs, maybe I'm on a different version of the documents or they haven't updated it yet and they're about to. But if you're getting errors, just straight up go into your environment or into the GitHub or wherever you are and just look at the source code and see what each function does to see what you're trying to do, because sometimes things be moving fast out here and we're just trying to build our apps in peace. So just word of the wise, I would definitely try to read the source code as much as you can and stay up to date because it is moving fast. The next thing we're going to do is we're going to set the index ID to compare contrast, so it knows it's about comparing and contrasting. And then we are going to add a predictor to our decomposed transform. So this is what I was talking about. So the decomposed query transform is that thing that's going to go like, oh, I need to think of what other information I need to find before I can even answer this question. Like, I'm comparing and contrasting things. I need to have that a priori knowledge within my context before I can continue, because there's no point in me answering a question about anything I don't know. So yeah, that's why we do it. And the next thing we're going to do is we're going to define a custom query engine. So we are going through each of the vector indices values, and we are going to get the query engine from each vector index. So the vector store index class has a function as query engine, and now you have a query engine which you can then use to pass in here. So transform query engine, and we're creating our own custom one in here. Custom query engine index ID equals the query engine, and we are setting a custom query engine for the graph as well. So we're getting our query engines for each index and the graph, which is composed over the indices as well, because we have those two use cases again. So again, like just reiterating the point, the reason we want to have a unified query wrapper around our indices is so we can add more use cases to that abstraction. So I can, what you'll see in the demo is I'll be able to compare and contrast the cities, but also ask about specific questions as well and get pretty decent answers. And so the next thing we're doing is we are getting our query engine here, and we're returning it with the index summaries. And now we are going to define the router query engine. And for this, we're passing in all the info we need. This can be the titles again, the vector indices, index summaries, service context, and the graph query engine. You're going to see in a second why. If we go up to this function, we are going to be creating query engine tools. And we're importing that again from Llama Index up here. And so we are going to iterate over all the titles of the Wikipedia articles to get the corresponding key for the mappings of vector indices and index summaries. We're going to get the index and the summary of those, and then we're going to create the query engine from it so we can then build our vector tool. So for each vector, we're building a query engine tool that takes in the query engine and then a summary. So it knows what the query engine tool is for, and then we're appending it onto the query engine tools array. And then we are going to be creating a query engine tool for the graph as well. And we're going to be appending that onto the query engine tools array as well. And now with all of our query engine tools in the array, we can create our router query engine. So the router query engine is what is used to determine which tool is best to use based on the query. So this is before it has knowledge of the documents or anything like that. It's just saying, like, based on my knowledge of the summaries of the indices and what this query is saying, I'm going to be sending the query this direction or that direction. And we're returning the query router engine, or the router query engine. Ugh, it's a mouthful. And yeah, so I've had this loaded up right here. Just entered a question, and you can see what I did from the last one. I said, compare and contrast the arts and culture of Houston and Boston. You can see the outputs of it just asking, all right, what are some notable cultural institutions or events in Austin? And then it, called LangChain and I guess got a bad response and then tried again. And then it gave me this lovely response down here that said, Houston and Boston both have notable culture institutions. Boston is known for a symphony of orchestra, ballet, opera company, book festival arts. You get the gist. So maybe I could say, and so we're saying compare and contrast the sports in Toronto and Houston, and we'll see what it comes up with. What are some popular sports teams in Houston? So you can see it's breaking up the query. And hopefully it can give us a response. Toronto and Houston both have popular sports teams in various professional leagues. However, Toronto has a National Hockey League team, the Toronto Maple Leafs, which Houston does not have. Houston has teams in every other major professional league, including Houston Astros, MLB, NBA. Oh, goodness. Both cities have had their success in respective sports, with Toronto Maple Leafs and Houston Astros winning championships in their respective leagues. Wow, that is a very nice thing to do. Not trying to belittle one city over the other, but just saying they're different in their own way, and that's what makes them special, and that's why we love them. Well, that is the video. That's kind of the end. If you liked this walkthrough and me kind of talking about why we need to have, or why it's nice to have unified query abstractions over your indices, let me know. Give me hate comments, love comments, like comments, questions, concerns, and yeah, join the Friday Lunch Discord. But there's no outro, so goodbye.